In the next sessions, we'll be talking about a classifier called classification and regression trees. It's also sometimes called CART. Classification trees are sometimes also called decision trees, which is very confusing because the term decision trees is also used to describe a completely different technique that's unrelated to data mining. So what are classification trees? First of all, they're automated and data-driven, similar to k-nearest neighbors and naive Bayes. But in contrast to those two methods, trees create understandable rules and are therefore not black boxes. They allow us to actually understand how the inputs affect the output, which inputs and how they affect the output. And also, they're very easy to interpret and therefore useful for presenting to upper management. We're going to talk about using trees for classification and for profiling, in other words, for explaining and for predicting. And we'll also see that we can use trees not only for classification or categorical Y, but also for prediction in a numerical Y. Trees are awfully common in a wide variety of applications. You'll find them especially in applications where you need this transparency of how the X's affect the Y. Examples are credit risk assessment, or a nice example from the book Data Mining Techniques by Barry and Linoff is health insurance underwriting, where you need to show that coverage denial is not based on discrimination. You can't just tell the person, sorry, you're denied because that's what the algorithm told us, but instead you have to tell them exactly why they did not qualify. And if we're talking about health insurance, we might as well have a small humorous moment about health insurance in the United States. So on a more serious note, let's look at a scatter plot of two predictors, and we're using color to denote an outcome of interest. Here we're looking at customers, and their output of interest is whether they prefer regular beer or light beer. We're using two predictors, age and income, and the question is, how does a tree help us split the light and regular beer drinkers? A tree does this by splitting, in this case, the 2D area into rectangles. And it looks for splits on the predictors that create homogeneous groups in terms of having a majority of either regular beer drinkers or light beer drinkers. The tree will create multiple splits, such as these here, where in some of the rectangles we have a big majority of, say, regular beer drinkers, whereas in others we have, again, a majority of light beer drinkers. So we're trying to create areas in the predictor space that has mostly one of our classes of interest. Let's look at an example where, again, we're looking at beer preference, and we have a beer manufacturer who wants to build a real-time predictive model for beer preference. He's going to use the customer demographics in order to serve the right beer. So think of an automated bartender where you walk into the bar, and based on your demographics, say your gender and your age group, you're going to be served a certain beer, and hopefully this is going to be indeed the beer that you prefer. The data that we'll use is a small data set. It contains 100 records, and our goal is to classify the preference of new beer drinkers. So this is a predictive task. We have a bunch of demographics. The gender, one is male, marital status, one is married, income level, age in years, and here's our output of interest, has two classes, light or regular. Let's first look at the output of a tree so that you can get a sense of how simple it is to understand what's going on and how transparent it is. We start reading a tree from the top to the bottom. The round circles here are called splits. And what we do here is basically translate the cuts, the horizontal and vertical cuts that we saw in the scatter plot into a tree structure. The reason is that with a tree, we can show splits on many more than just two predictors. The top split here is on age, and it's telling us that we want to split all our records in the training set into people who are younger than 42 and a half, and they would go left, and people who are older than 42 and a half years old, and they would go right. Software will usually have an option to either hover over this node, or it will have some text telling you which direction of the tree is for the higher numbers and which one is for the lower numbers. After we split on age and we look at the older people, you'll see we have a split on income level. And again, if your income is below this value, you go left, otherwise you go right. And you keep going down the tree. At the end of the tree, we have leaf nodes or terminal nodes. And these nodes contain a set of records that are supposed to have a majority, a great majority hopefully, of one of these classes. And that's why you see a label such as regular or light beer. That's the majority class in each one of these nodes. What we can see here is that we see not only which predictors are playing a role in the prediction, we also see which predictors are not playing a role. Even though I ran my model on the entire set of predictors, we only see age and income showing up in this tree. The other piece of information is that we know the exact splitting values that are informative to predicting the label. The last piece of information here is the number of records that we have within each subset. So for instance, this group is based on 31 records. It also means that here we only have 7 records, and we have to think carefully what is a minimum number of records that we feel sufficiently comfortable that the result is. We will talk about overfitting later on. We can evaluate the performance of trees in the ordinary way by looking at confusion matrices if we're trying to classify, or if we're trying to rank, we can generate lift charts. Obviously, we would not want both of them in the same case because each one depends on your objective. Let's look now at how we grow a tree. In order to start a tree, we're going to have to choose which predictor to split on and on what value to split. In order to determine that, we're going to have to define what is a best split. So a best split is going to take a group of records and break them down into 2 subgroups so that we have hopefully more of a majority of one class in the resulting children nodes. Now, what the tree algorithm does is it examines each and every one of the predictors, and not only that, for each predictor, it's going to look at every possible split value. So if I'm looking at age, I'm going to look at every possible age to split on to create 2 age groups. And then we're going to choose the split that maximizes the reduction in impurity of a node. In other words, we're looking for the split that creates the most homogeneous subgroups. Each one of the subgroups is going to be homogeneous. There are a bunch of different algorithms. You might have heard buzzwords such as CART and C4.5 and C5. And these are different ways to implement the tree algorithm by different software packages. One difference, for example, is that while CART always will split into 2 nodes, in C4.5, we can split a certain node into more than 2 splits. And then we'll get things that look more like bushes than like trees. Next thing, we're going to have to determine what is purity. If you remember when we talked about homogeneity in the context of clustering, which is unsupervised learning. Here we're trying to talk about homogeneity in terms of supervised learning, where homogeneity is measured in terms of the Y, in terms of the mix of the classes. We're going to look at 2 very popular impurity measures. One's called entropy and the other is called Gini index. Usually you can choose between these 2 in the software, or maybe your software implements one of them. So to give you a feel what the entropy measure is. The entropy of a node, or a collection of records, is simply defined by this equation. K is the number of classes, so in the beer example it's 2, and Pi is the proportion of records in class I. So all we need to know is for that group of records, what percentage belongs to each class. Now notice that we have a logarithm base 2 here, which, to remind you, it means we're looking for the power so that 2 to that power is equal to the number. The entropy can range between 0 and log base 2 of K. It will be 0 when we have only one class in that group, if we have only light beer drinkers or only regular beer drinkers, and that is the purest level. So an ideal split will actually create an entropy of 0. On the other extreme, we have the most possible mixed group. If we have 2 classes, we'll have a 50-50 breakdown, and that will give us a log base 2 of 2, which in this case would be equal to 1. So the idea is to compute all the entropies for all the different possible splits, and then rank them and choose the one that's best. Here's a pictorial view of what the entropy looks like as a function of the breakdown of the 2 classes in a problem. As we have completely one class dominate the entire group, we have a very low entropy all the way down to 0. And it starts becoming more and more heterogeneous as we have the full 50-50% where the entropy gains the value of 1. Let's look at a tiny example. Suppose we have two classes. It could be light beer and regular beer, hire, don't hire, accept, don't accept. And in this case, the entropy is going to run between 0 and 1, where 1 is the worst case. If we have 50-50% breakdown between the two classes, as shown in this little circle, then our entropy will be 0.5 times log base 2 of 0.5, and again, add up that number. We get an entropy of 1, which is again the worst case. On the other hand, if everyone is only of one class, then we get an entropy value of 0. How do we use this entropy measure in a tree? We start by looking at the node that is not split, and we compute the entropy of that node. Then we perform the split and we get two children nodes. We're going to compute the entropy for each one of these children nodes. And finally, we'll combine these two children node entropy values by taking a weighted average. The weights will simply be the sample size of each one of these record buckets. Let's look at an example. Suppose we start with 100 beer drinkers where they're broken down 50-50 into regular beer drinkers and light beer drinkers. Now the question is, should we split these 100 people by gender? Does this actually improve our homogeneity? So we break down the 100 people, 57 are males and 43 are females, and here's the breakdown of their preferences. Stop the video for a minute and see if you can figure out whether we've reduced impurity by including this gender split or not. All right, let's look at the computation of entropy. So originally we have 100 people and broken down exactly 50-50, which means the original entropy is 1. What happens when we look at the females? When we look at the female node, we have 25 out of the 43 preferring light beer, so we have 25 over 33 times logarithm base 2 of that number, and we have 18 over 43 preferring the light beer, so we do the same thing with that number. And when you add up all these numbers and take a negative sign, we get an entropy of 0.98. We can do a similar computation for the male node, and we'll get an entropy of 0.989. Finally, we combine these two children nodes by taking a weighted average of their entropies, and the weights are the sizes, or in other words, the number of records in each one of these children nodes. The combined children entropy is 0.985. Indeed, this is below 1, which was before the split. But is this actually a useful reduction? That's, of course, a question that we're going to have to ask in terms of prediction. Is our predictive ability going to be better when we introduce this split compared to not introducing it? However, we'd still use this 0.985 in order to compare this split to other possible splits and choose the one that seems the most promising. There's also a different type of impurity measure called the Gini index, and it's very similar to the entropy, except that it has a slightly different formula. So the Gini index is again just a function of these proportion or percentage of records in each class. And K is again the number of classes. The Gini index can obtain values between 0 and K minus 1 over K. When it's 0, this is similar to the entropy metric, we have a group of people who are all belonging to the same class. So that's the best case. When we have a completely mixed group, say if we have two classes, then we'll have a Gini index of half, indicating that this is the worst mix that we can obtain. Let's also just do a simple example with a Gini index. So again, we'll look at the same split by gender and ask ourselves which Gini index is going to be higher, the one for the females or the one for the males. So how do we do the computation? Once again, we're going to use the probabilities based on 25 over 43 for females and square that, and 18 over 43 in the female node, square that, add everything up and subtract it from 1, and we get a Gini index of 0.487. We can do the same thing for males, and we see that the Gini index for females is lower, indicating that that node is more pure, more homogeneous. In the next sessions, we're going to look at two very important aspects of trees. One is, how do we use the tree? How do we classify new records? And in fact, that's not going to be the only use. we'll see that we can also use it for variable selection. The other issue, which is going to be critical, is avoiding overfitting. Because if we just keep splitting and splitting and splitting, we're easily going to overfit our training data. And it turns out that there's a very nice trick in order to create a tree that doesn't overfit your training data.